String art is a form of craft characterized by stringing threads between nails hammered onto a board. Basically, you have a board with hundreds of nails hammered onto it. Starting at a random nail, you proceed from one nail to another, non-stop, until you end up with something that looks like what you wanted to create. It is not very difficult to come up with the sequence of nails to produce a fairly simple piece of art like the one you see on the screen right now. I would actually encourage you to pause the video right now and spend some time coming up with a nail sequencing scheme to recreate the string art on the screen. I can all but guarantee you that it is not a difficult exercise. It will take some time, but it is fairly easy to do. But if I were to ask you to take the picture on the left and produce a string art that photorealistically recreates it like the picture on the right, then the task would be almost impossible for most of us who is not an actual computer. So in this video, I'll present to you how we can use simple mathematics, not more complicated than trigonometry, to come up with an algorithm to generate string art using a digital computer. Throughout this video, I'll be using the C programming language to implement the algorithm. Before we even begin to approach the problem of coming up with an algorithm for the string art, it is necessary to understand how computers store and display images. After all, it is these digital images on top of which we will be building our algorithm. So let's see how digital computer imagery works. The physical display you are looking at right now is made up of a grid of millions of these little squares called pixels. The computer I'm using to make this video right now can display a grid that spans 1280 pixels horizontally and 1024 pixels vertically, adding up to a grand total of about 1.3 million pixels on the screen right now. If you zoom in one of these pixels, you will see that it is made of three different colors, red, green, and blue. The way a pixel works is by adjusting the contrast of these colors and the fact that you would be looking at it from a distance large enough to not be able to tell apart individual pixels. We can obtain almost any color by manipulating the values of the intensities of each individual color channel. On one end of the spectrum, we have the color black, where the intensity of each color's channel is set to its minimum, 0 as you can see here. And on the other end of the spectrum, we can obtain the color white by setting the intensities of all three color channels to their maximum. And any color in between can be obtained by manipulating the values between these extremities. As a consequence of this display scheme, computer image files also store image data as a list of pixels, with each pixel of color being made up of three numbers that go from 0 to 255. We will see why those numbers go from 0 to 255 and not any other number in a while when we manipulate some images. For the purpose of this video, we'll only be working with grayscale images and not color images because it makes our job much easier while not taking anything away from what we have set out to learn. So as the first step, let's convert some color images to grayscale. There are many digital image formats to work with, but today we will be using one of the simplest of those, the BMP file format for images. The BMP file has two main parts in it, the header and the pixel array. The header consists of metadata pertaining to the image, such as the image width, image height, colors used, etc. The pixel array, which is the meat of the file, is where the image data could be found. So let's take a closer look. To manipulate pixel information, we need to know where the pixel information is located inside the file and how many pixels are there. Going through the BMP file format, we can see that the metadata about the image could be found at different file offsets from the beginning of the file, and in particular, the pixel array offset could be found at the 10th byte offset from the beginning of the file. Similarly, we can obtain the pixel array width and height information metadata from a byte offset of 18 bytes and 22 bytes respectively from the beginning of the file. The description also talks about how individual pixels are stored in the pixel array, and it is necessary to understand how each individual pixel is mapped in the grid of the pixel matrix. It basically says that the pixel array is an array of bytes that defines the bitmap bits. These are the actual image data represented by consecutive rows or scan lines of the bitmap and so on and so forth. Here in the end, it also says this particular sentence. The system maps pixels beginning with the bottom scan line of the rectangular region and end with the top scan line. Let us see what that means. While a picture is displayed as a two-dimensional structure on the screen of your display, It is not actually stored as a two-dimensional structure inside the image file itself. It is actually stored as a continuous stream of consecutive bytes inside the file. This situation dictates that an individual pixel in the grid at a particular row and a column be mapped to a particular offset of the image file's pixel array. In a BMP file, we start at the pixel in the bottom left corner of the image and move to the right. At the end of each row, we move to the row above it. We do that till we finish at the top right corner, all the while storing each pixel in the image file's pixel array in a linear fashion. I think we are ready to write a program to convert color images to grayscale. But first, we'll write a program that makes a copy of an image file, and we'll go from there. We'll open the BMP image file whose file name is supplied to the program as an argument and acquire the pixel array offset first. The pixel array offset is at the 10th byte offset from the beginning of the file and is 4 bytes wide, which would fit inside a uint32t type, which is also 4 bytes wide. Conveniently, the pixel array offset gives us the size of the metadata of the file because everything before the pixel array is the image metadata. We will use this fact by allocating enough memory to accommodate the metadata and copying the contents of the image file from the beginning of the file till the pixel array offset. We will later dump this data into the copy file. Next, we'll acquire the image width and height at the byte offset of 18 from the start of the image file. Both of them are 4 bytes wide and we'll use them to calculate the size of the pixel array or the image size. We'll also print some diagnostic messages to know a thing or two which we care about the image. And also, let's not forget to clean up after ourselves. The size of the pixel array is calculated as the product of the image width and height, the number 3 because each pixel is made of 3 different colors, and the size of the data type that holds the value of each color, which happens to be a byte. We have the memory allocated for the pixel array, and we will read the image data into the pixel array in one shot. At this point, we have copied all data from the source image file and we are gonna dump this data into a new file. I'll call this image copy image and dump all data from the source image file into it in a single shot. We'll compile the program and run it with an argument and we have a segmentation fault. That's classic C program for you. Well, it turns out I forgot to allocate memory for the pixel array. So let's fix that and try again. Looks like we have a problem. It seems to be missing something. This is the original image I tried to copy to another file, but something clearly went off. Well, the problem turns out to be that a pixel is not in fact made of 3 color channels like I mentioned earlier, but 4. A fourth alpha channel is present in each pixel which controls the transparency of the pixel. A value of 255 alpha indicates that the pixel is completely opaque, and conversely, a value of 0 would render it completely transparent. We don't have to worry about this for what we have set out to do, and so we will just leave it alone. We will compile and run the program only to find that we have still got problems. It looks like I have got the wrong variable here, so let's fix that and run the program. It works. We have successfully copied the image file and therefore next we will see how to convert the color image into a grayscale one. So how do we take a color pixel and make it grayscale? Remember the part when I said if the color intensities of all 3 channels are set to 0, the resulting color would be black, and if the intensities were set to the maximum, the resulting color would be white. We can get a clue from this using the fact that gray is but a shade of color between black and white. So let's see if we can equalize the values of each color channel in a pixel and get a shade of gray. In the previous program, before we dump the pixel array into the copy file, We will iterate through the entire pixel array, and for each pixel, we are going to sum the value of three color channels, take the average, and put them back to those color channels. This way, each color channel holds the same value, which is the average of the three earlier colors. This should work pretty well, so let's check it out. Looks like it works, and we have a grayscale image. But not so fast. It turns out the human eye does not respond equally to the three base colors, and therefore taking the average of the three colors with equal weights is not the best way to do it. Researchers have come up with different weights to each of those colors after many experiments, which gives a better results apparently. So let's use that formula to upgrade our program for a better effect. So let's do that. We will start by adding the math library and fix the weights on these color channels, round the values, save the program, compile it, and see what happens. I don't know if you could notice, but this one definitely looks lighter and better overall compared to the previous one where we used equal weights for each color. So with that, we shall call it a day and end this video. In the next video, we will begin to draw up a strategy to develop the algorithm for the string art generation.